In this video, we're going to look at an example of Newton's second law in which we have two blocks right here attached to a rope, right? And we have a pulley. And also this surface right here has friction, right? We're going to say that the mass of this block is m1, the mass of this block is m2, and the mass of our pulley, right, it's massless. All right, we're going to say that this pulley right here is a massless and frictionless pulley, which means the pulley only determines the direction that the system moves towards. And basically what's going to happen is this block's going to pull downward, right? Its weight is going to pull it downward, and overall the system's going to move in this overall direction. Right, so this right here is the overall direction of the system, basically. That's the idea. The pulley only determines the direction of the system, has no effect other than determining the direction that the system moves towards. Okay. Also, we have a surface with friction. We're going to assume the system does move, so we have kinetic friction. We're going to say kinetic friction is just, our coefficient of kinetic friction is just mu k. And so this is basically the three things that we're given, right? So we're going to write right here. We're given m1, m2, and mu k. Right? So that's basically the three things we're given. And our goal, right, usually in problems like this, is to find the acceleration of the system. So that's what we want to find. We want to find the acceleration of the system. And we know to do this, we gotta pretty much look at the forces acting on both of our blocks. So basically the forces acting on block 1, right, and the forces acting on block 2. So what do? Well, basically starting with block 1, what's the forces acting on block 1? Well, what force is causing block 1 to move to the right? Because we know that the system's overall going to accelerate in this overall direction. Well, what force is causing block 1 to move to the right? It's the tension in the rope, isn't it? Right? There's tension in the rope, and the rope is pulling m1 to the right. And so we're just going to label this rope, this force as the tension force, and it's pulling m1 to the right. But what's causing that tension force? What's causing the rope to pull m1? But really, it's not the pulley because it's massless and frictionless. It has no mass, so it can't be the pulley doing it, right? It's m2, right? When m2's weight pulls downward, the rope pulls m1 to the right. So really, it's m2 pulling on m1 with that tension force. Now, if m2 pulls on m1, then m1 is going to pull back on m2. That same magnitude of force, just in the opposite direction of the overall motion of the system. This is just a case of a third law pair, right? Which tension, that's the idea. So really, it's the tension force that's causing m1 to move to the right. Right, so really we have a tension force. Okay, also, we have friction, right? So friction, we know, since the system's going to move this way, friction will act in the opposite direction. So really, we have friction, F1K, right? The kinetic friction acting on block 1 going to the left. Of course, M1 has a weight force downward, M1G, and of course, it's on the surface, so normal force pointing upward. So F1N. This is basically the forces acting on block 1. Now, the forces acting on block 2. Of course, we have a tension force, as we kind of just labeled, right? The tension force, that M1 is pulling back on M2, right? So we have that tension force pointing upward. And also, I mean, what's causing the overall, like the direction system to point downward? Well, it's M2's weight, right? M2 has a weight force pointing downward like this. And so this right here is basically the forces acting on both of our blocks. So now that we have the forces acting on our blocks all labeled, now we need net force statements for both of our blocks, right? So we need to know the net force on block 1 and the net force on block 2. And remember, our goal is to solve for acceleration. So we're going to write net force statements that involve the accelerations of both of our blocks. So the acceleration of block 1, of course, it's to the right, isn't it? So it's to the right. Right, to the right. This is the direction of our acceleration of block 1. And the acceleration of block 2, it's downward, isn't it? So this is the direction of acceleration when it comes to block 2. So, starting with block 1, right? We're going to start by doing block 1. Right? Acceleration is only to the right. Block 1 is not going to move vertically, is it? Right? The normal force and the weight force, they cancel out. Meaning we're not focused on these two forces when it comes to writing our net force statement, right? Because the block doesn't accelerate vertically. So really the only forces we're concerned about in our net force statement are these two forces here, right? Because acceleration is horizontal for this block. So what that means is we're going to say that the net force is tension minus F1K. Tension minus F1K, right? Right? And the reason why we're saying it's tension minus F1K and not F1K minus T, right? The reason why we're doing this minus this is because the direction of the acceleration is to the right, and so we're saying that right is positive. So we're doing tension minus F1K, right? That's the idea. And for block 2, basically it's going to be M2G minus T, right? All right, M2G minus T. And because the reason why it's M2G minus T and not the other way around, because acceleration is downwards. So we're saying downwards is positive. So M2G minus T. That's pretty much it. Now we're gonna write these into as specific as we possibly can, right? Net force is just mass times acceleration. So really it's just M1A, right? Right, equals tension minus F1K. We know what kinetic friction is, right? Kinetic friction, if we recall, well, in general, kinetic friction, right? Kinetic friction in general. Why am I continuing to write F1K? I'm just trying to write FK, right? Kinetic friction in general is just mu K Fn, right? And so we can just use this idea to write what that is. It's just mu K F1N. Right, mu K F1N. That would be kinetic friction, right? We can continue writing this, right? Because we know that the normal force for block 1, these two are equal, aren't they? Because they cancel out. So really the idea is that F1N, right, F1N, that's equal to M1G because they have to cancel out, right? No movement in the vertical direction. So that's what we're going to replace that with. And so really, F1N is M1G. And so that's basically what we get from this. And this is as far as we can write it, right? This is as far as we can go with this net force equation, right? And moving on to our other one, for block 2, really it's saying net force is just mass times acceleration. So we just write M2A. And that's as far as we can go, right? We can't really go any further with writing this. So basically, notice what we have here. We have two unknown variables in both of our equations. So really, we have a system of equations. And basically, we could solve for the acceleration of our system, but we could also find the tension in this rope. So we're going to find actually both acceleration and the tension of the rope. And so what you could do, since this is a system of equations, we could let's just say solve for tension, and then substitute tension into here, and then just solve for acceleration. But the way I like to solve problems like these is I like to actually add these two equations together. And the reason why is because you can see how tension will cancel out. We can just solve for acceleration. So that's all we're going to do, right? We're just going to take this equation, right? M1A equals T minus mu K M1G. And we're going to add this equation to this equation, right? So we have M2A equals M2G minus T. We're adding these equations together, right? Because, and the reason why, the whole purpose of what we're doing is tension will cancel out and we can solve for acceleration, right? So when we add the left side of the equation, we get M1A plus M2A, right? M1A plus M2A. And on the right side of the equation is M2G minus mu K M1G. right? We could factor out acceleration. So a times m1 plus m2. And on the right side, we could factor out g, right? So we get g times m2 minus mu k m1. And then just solving for acceleration, we divide m1 plus m2 to the other side. And we get acceleration is just g times m2 minus mu k m1 all over m1 plus m2. And so this right here would be the acceleration of the system. That's basically the idea. And so we found the acceleration of the system. Now we could find the tension in the rope, right? Because basically we just have to go back to one of our original equations, substitute what we have for acceleration, and then we have tension. So we could just, let's just say we use this equation right here, right? Hopefully we have enough room. If we were to solve for tension, well, tension, if we solve for tension, it's going to be m2g minus m2a, right? We're solving for tension, that's what we would get. Right, to make this convenient for us, we're just going to factor out m2. Right, we're going to substitute what we have for acceleration into this equation. Right, we're going to substitute this in for acceleration. I think we'll have enough room. Right, g times m2 minus mu k m1 all over m1 plus m2. Yeah, that's basically what we have. And notice how we could factor out g from this, can't we? We can factor out g. And so this is actually pretty cool. Like we factor out g. It's not super cool, but we could factor out g. And what we get inside, what we get inside of our parentheses, right here we just get a 1. And right here we get m2 minus mu k m1 all over m1 plus m2. And so we could say this is our final answer, but we don't have to. We could actually keep going, interestingly enough. So what we're going to do is we're actually going to erase this stuff that we have right here, because I realize we're not going to have as much room, right? But we're not going to erase this equation because it's one of our original equations. And we're going to write this down here, right? A is just g times m2 minus mu k m1 all over m1 plus m2, and this is what we have, right? We can keep going for what we have for tension. We can keep going with this because it turns out we can actually combine these two things together into one fraction. So when we do that, basically we still have m2g, but in here we could say 1, right? We got to get the same denominator. So really 1 is just m1 plus m2 over m1 plus m2. And we're subtracting what we have here. So really subtracting m2 minus mu k m1 all over m1 plus m2. This is what we have. This is the same thing as this, right? We're going to combine these fractions now. Now we have to be careful when we're combining fractions, right? This is really important, because, or else you'll mess this up. It's kind of like a basic math mistake. Basically, we have m1 plus m2, but we have a minus sign, right? The minus sign here can trip people up. You have to subtract this entire thing right here. You're going to subtract parentheses what we have here, because we're subtracting this fraction. We're subtracting this expression right here. So subtracting m2 minus mu k m1 all over m1 plus m2. All right, so notice what we have here. Really, notice how m2 is going to cancel out with m2, right? Right? If we were to distribute the negative sign, then you can see how m2 and m2 would cancel out. And really, negative, negative, right? Two negatives make a positive. So at this point, we could just say that, right? Basically, we're going to move up to this in a single step. Basically, we can factor out m1 from this, and we get m1 times, basically right here, we're factoring out m1. So right here, we just go 1 plus mu k. Right, interesting, mu k plus 1, all right, divided by m1 plus m2. And so really, we're just going to write this right here. Tension is just, right, we can bring out m1 to right here. So it's just m1, m2g times, right, we can just write this as mu k plus 1 divided by m1 plus m2. And so this right here would be the tension in the rope. And that's really interesting, right, mu k plus 1. And yeah, this is basically the idea if we wanted to find the acceleration of our system and the tension in the rope. And that's pretty much the idea of solving a problem like this. And that's pretty much it.